So thank you for joining me, everyone. I am Joe Nash, and I'm a developer. You can follow me on Twitter at JNA_SH. And I'm a developer advocate at a company called Braintree. You can follow Braintree Dev, my team, at Braintree_dev. If you want an example of using those Twitter handles together in a sentence, #Topconf Braintree Dev, Joe Nash is awesome. If you do that, my manager will think I'm doing a good job, which is always nice. So, I just want to say thank you for having me. It's always awesome to come to places like Estonia to talk. I've never been here before. And kind of doing this for a living, it's really nice to come to some place that's totally different, like walking around town. I mean, I know the other people who do this sort of thing have been saying this place is really cool. Having spoken 32 times in 12 countries this year, make that 13 countries this year, it's just been a really pleasant experience, and you've been amazing as a conference. I think it's been a really nice conference. So one thing you may have already noticed is that I'm very like this. Lots of words and lots of hand movements. I do run an open heckle policy, so if I do talk too fast and you're struggling with what I'm saying, in general I say something, oh, I've lost mine. Oh, muted.
On top.
There we go. Awesome. So if I do talk too fast and you lose what I'm saying, or I just say something that makes no sense, please feel free to call me on it. I will try and correct myself. So, onto the talk. This is a bit of an experience report. We're going to be talking about a journey through some cool technology that took place at Braintree. Braintree has always traditionally been a Ruby shop. And as a Ruby shop, we have problems with data because Ruby's just not very good at it. So we're going to be talking about how we can overcome those problems, and that involves a lot of technology called Kafka. Who's heard of Kafka? Who's using Kafka? Okay, cool, just the one, perfect, that's what I like. And obviously a little bit of closure because we're in the not only OO track. I will say though that this is not a closure tutorial. I don't expect people to be walking away from this understanding how to use closure, but I would hope that you can walk away from this with a cool story. You can go to your managers, you can go to your bosses, and you can say, hey, Clojure's really cool, Kafka's really cool, we should be using this. So I'm hoping that will expand some minds. We've got the obligatory Adventure Time GIF, which I will sit here for the entire duration of while we finish it, because it's really cool. And back to, oh no, it takes too long, never mind. So, why should I be giving this talk? There we go. My clicker stopped working. What is going on? There we go. So why should I be giving this talk and not one of the engineers, not a Braintree, someone who worked on this stack? So I'm a collector of cool technical stories. As a developer advocate, I try to find whatever cool hacks I can, because I absolutely love hacks. I love janky solutions. This solution is actually a very good solution, so it's slightly outside my usual sphere of interest. But the reason I like this solution is that it gave us a lot of new insights. And I love new insights, especially when they pertain to functional programming. Anyone who came to my talk this morning is obviously I'm very into Haskell, I'm very into crazy functional languages. And Braintree being a Rails shop, sometimes I get a bit bored inside Braintree. Like I'm walking around and be like, oh, that's a nice credit card form. Those are good. I like those. So every year we have what's called Topconf, where all of Braintree get together and we hear from the product team about the cool stuff they're doing. It's an internal conference, it's really neat. And last time I was out there, going out to our main office in Chicago, I thought, okay, I'm going to walk around, talk to the engineers, and see what crazy rogue stuff is going on, see where the polyglottism that our company has is really coming out. And I found a lot of people doing Go, and Go is nice if you like a language which is essentially saying, we've learned a lot over the last 20 years about programming language design, let's ignore all of that. So I looked at that and was like, okay, that's new. And then there's one guy doing Haskell, it's a build script for an internal tool. But he's trying. It's about 20 lines, but I appreciate that. And then I found that there's a lot of people doing Clojure. And not only are they doing Clojure, I say a lot of people, it's about 8. Not only are they doing Clojure, but they're doing Clojure for what is a very important part of our stack. So I'm going to tell you a bit about that, how we got to where it is now, how this Clojure got in, how we decided to use Clojure, and then a bit about how we actually architected that and what we're building. So, but first, I need to kind of tell you what Braintree is, explain the problem space, that sort of thing. So Braintree, anyone heard of Braintree? Obviously you two have, but excellent. So this is good. So Braintree, okay, who's heard of PayPal? Cool, you must have heard of PayPal. Perfect, there we go. So Braintree, we are a payments processor and we are owned by PayPal. It was our anniversary about 3 months ago. We got acquired about 2 years ago. It's pretty cool. So Braintree, we do something a bit different from PayPal, in that is we offer kind of a method agnostic payment form. So this is a Braintree merchant, this is Flick. They're a really cool startup based out of Stockholm who make this really neat IoT device. It's a Bluetooth Low Energy button. There's actually 2 of them stuck to the wall, one with a like sign, one with a dislike sign. Hopefully if they work this time, you'll be able to tell me if you like my talk or not at the end. So they're pretty neat. But this form here, this is a Braintree form. So Braintree, we provide a drop-in form that does some really neat stuff. So we do a lot of use of technology called tokenization, which is how we enable you to take PayPal, credit card, Bitcoin, Apple Pay, Android Pay, anything you want, all in one form. Anyway, so that's pretty neat. We have some crazy clients. We have Uber, Airbnb. If any of you have children, I'm sorry, but I took your money. And with those, we take a lot of data. So does anyone know how many rides Uber is doing a day right now? Well, as about a year ago. All of them, pretty much 1 million rides a day, and that was as of November 2014. And since then, they've expanded into China, they've reached a lot of new markets, they're doing a shed load of data, and that's all coming through us. If we look at the amount of payments that PayPal are doing within their entire system, that's 1.16 billion this year, which was up 25% year on year. They're growing enormously. 1 in 6 payments is facilitated by PayPal, and that includes the Braintree figures. And if we look at Braintree in isolation, we see that we've done 50 billion in payment volume in 2015. And also, this is an interesting fact, this one, the amount of cards we've stored on file has increased by 118%. We're up to 154 million cards stored in our databases, which is just ludicrous and vast amounts of data. So we need to build a real-time data pipeline to deal with this data, and that is where the story comes in. So, as a payments processor, we have one priority, and that is to keep processing payments. Obviously, if we stop processing payments for a minute, that is loads of Uber rides aren't getting checked. That's loads of kids who can't get their Minecraft copy, and that's a disaster. So we need to keep the money flowing. We need to keep making sure that dough is flying off the hands into the butt of the turkey. So to do that, we need a primary database. Obviously, what's going on with this clicker? Obviously, there we go. Obviously, as transactions take place, we need to store those immediately. We need to make sure that that transaction is stored, that it's taken place, that we have the credit card details, that we have the address, etc. But then we also need a data warehouse because, well, for a couple of reasons. The first and most important one is backup and duplication. Obviously, having a data warehouse is good practice, especially if you're a payments processor and you're holding so much sensitive data, because we don't want to lose that data, right? If our primary DB goes down, how many transactions are we going to be losing? We're going to be trashing Uber's tax reports. We're going to be potentially losing addresses before the items are being shipped, etc. But that's not the most interesting reason. The more important one is that it acts as a single source of truth. When we talk about a data warehouse, we're talking about a system that is aside from the primary DB, which we can do things like search requests against, we can run reports against it. We want these things to be separate from the primary DB so that we have a low impact to live transactions. If we're running like massive searches for tax reporting reasons against the primary database, we could potentially impact our ability to take live transactions, which is disastrous. That's not what we want to do. So our data warehouse is built with Amazon Redshift. If you're not familiar with Amazon Redshift, it is essentially a gigantic Postgres instance built by Amazon. Well, it's built by Amazon. It's kind of an open source technology now. It's a distributed Postgres that provides an API as a single machine. So it appears you're just making queries against one Postgres database, but in fact, it's many distributed over loads of machines. It's absolutely great. It's fantastic. And we use that to make a complete mirror image of our primary database, which is Postgres. And how we were doing this traditionally is through batch processes. Obviously, being a Rails shop, whenever we run a migration, we automatically get our updated at and created that column within our data. So we would just come along every day or so, and we'd say, okay, check all the updated at columns. Are they different from yesterday? Run this massive batch process and move it from the primary over to the mirror, over to the data warehouse. And that's an awful way of doing things, because batch updates have a couple of issues. Okay, so the first issue is that they're slow. So already we're talking like with this amount of data, we're talking 8 to 12 hours, and that's just a stupid amount of time to wait for this data to be where it should be. But then they're also unpredictable. We can't actually guarantee how long that's going to take, especially if, for example, South by Southwest is happening over in Austin. If South by Southwest happens, Uber have a massive day, they make so many more transactions than normal, that can impact the amount of time this batch process takes by hours. So if we've got data engineers who are waiting to get at the data warehouse to run some reporting, to do whatever it is that data engineers do, and we can't tell them when the data will be there, that's going to be awful for everyone. And we can't track deletes. Because we're using this updated that and created that column in the rows for the transactions, etc., if we've deleted some data, there's no updated that and created that column. So you potentially end up with this ghost data just floating around in the warehouse. And then we also have the other end. We have missed updates. If we have some data which we want to put in there that hasn't gone through the Rails migration, that has come in through a different way, if we're backfilling, etc., we don't necessarily have the correct data in that updated that and created that column, so we lose those updates. And all these things, all these issues of batch processes and with how the data moves from one system to another, resulted in a burden of knowledge. If you had to work with any of our data in the data warehouse, you suddenly had to understand all these potential problems. You had non-technical people who had to get at this data, who suddenly had to become database engineers to understand why they couldn't work when they wanted to work, which is absolutely awful. On the other end, we have problems with search. So Braintree runs a really awesome search dashboard. We have like this huge thing, checkboxes everywhere. There's also this drop down here with 50 fields you can do partial text matching on. And in theory, we were saying to merchants, hey, you can come and search against all of your data, against all of these fields for all of time. In reality, what is happening when you do this is this constructs a massive SQL query and just throws it at the live database. What? So when you had merchants like Uber and they were saying, oh, hey, I want 7 days worth of data, we're like, cool, 7 days, chill, big SQL query against the database. Oh my word, that is more transactions than we can return before the request times out. So the request was timing out, they weren't getting the searches, so we were like, okay, just scope your queries down. And then it got to the point where some merchants were having to scope their queries down to like hourly queries and running those for like 24-hour periods against a whole week's worth of data just to get what they wanted, which is absolutely appallingly awful. So we wanted to fix it so that they can do the size of search they wanted, so that we weren't having to tell them, oh yeah, just do a smaller query and do lots of them. So we had to restructure that as well. So we look at our architecture right now. We're looking at this sort of setup. So we've got a primary DB, which is feeding into a batch process, which feeds into Redshift data warehouse, and that feeds into our transaction search. What we really want is something closer to this. We have a primary DB, we have a Redshift data warehouse, and then we were looking to change to Elasticsearch because this huge SQL blob was just not really doing it for us. So we have this magical question mark in the middle, which leads usually to profit, but in this case is leading to data. So the data engineers got together, and at the time there was 5 of them, and the 3 of them were called David. So David's got together, and they started talking about possible ways around this. And the first one they came up with was logical decoding. So Postgres does this really neat thing with synchronous replication, which one of the Davids was really hoping we could tap into and just pull the events out live from Postgres and just feed them into a queue and send them along their way and use that to mirror the database. But the main issue is that wasn't available till Postgres 9.4, which is now available. So now if you want to do this sort of thing, if you want to make a mirror of a Postgres database, you can tap straight into the synchronous replication log and just pull out those events and do what you want with them, which is really neat. But when we built the system, that was about 2 years away. And right now, that's still not stable. You're looking at about another 6 months before you realistically want to use this for anything important. So we're looking for alternatives. That's when we came up with PGQ. So PGQ, very imaginatively, is a queuing system built on top of Postgres. And PGQ does some really neat things. So first of all, it doesn't block live transactions. Anything that happens in the database is sent out as an independent event. It has nothing to do with the commits on that database or anything like that. It's completely independent. You can poll those events and do whatever you want with them. It then has really nice ACID semantics, which is obviously very important. If a commit doesn't make it through to the final Postgres database and doesn't make it to disk, the event isn't created in PGQ, which is perfect. Then obviously, there's another problem at the end of the system. Although we had a potential queuing system that looked like it worked for us, on the other end, instead of just having our data warehouse, we now also have Elasticsearch, which gives us another place to sync the data. So we're now not dealing with 2 places to sync this data, we're dealing with 1 place to sync this data, we're dealing with 2. And the interesting thing, which we'll come to later, is that these are potentially different shapes of data. Our data warehouse needs to be a complete mirror of the of everything in the primary DB. It needs to be the same database. But Elasticsearch, we're dealing with much more with the actual the semantics of that data. We're dealing more with the domain-specific things about the data. Has a transaction been created? Has it been refunded? Etc. So, but we started dabbling with PGQ, so we get to this kind of setup. And this is where we ran into an interesting problem with PGQ, in that PGQ, this doesn't seem like it should be a problem, but it is a problem. PGQ prioritizes database integrity. So PGQ, how that actually works is it creates another table in your Postgres database and just tracks the events in that table on the same disk, in the same place as your other Postgres database. So if the queue starts to get quite big, obviously that risk has the potential to bring your database down if you run out of space. So PGQ just dumps data really quickly. It lets go of it after 30 seconds. That is the default. There is no way to change it. So we have huge potential for lost messages. If our consumers go down for whatever amount of time, or they're not grabbing that data fast enough, we just start losing transactions and they never make it over to our replicated system. They never make it to the warehouse, they never make it to Elasticsearch. So we have this problem of where do we persist those messages? Is there some way, could we write a consumer which would have very low probability of going down that was putting those messages into another queuing system or something like that? And it turns out we could. Here comes Kafka. So Kafka, if you haven't heard of it, oh, hello. That was weird. Kafka, if you haven't heard of it, is an Apache LinkedIn project. So LinkedIn made it and then gave it off to Apache. And it does some crazy things. So here's a really ugly slide, but just focus on the green. So in July 2013, this is a quote from LinkedIn from about 3 months ago. It's an article. LinkedIn were processing 200 billion messages per day through Kafka, through their Kafka system. If we look at this year, 1 trillion messages per day with peaks of 4.5 messages a second. 1 trillion a day on LinkedIn. Who is using where are they getting that data from? That's a lot of recruitment spam. Like, what on earth? So when we talk, obviously that's a really impressive feat. That's an amazing thing. This system sounds like it's going to be really cool, right? So when we talk about Kafka, we're talking about a pub-sub meshing system that looks a bit like this. So very naive diagram. You have a Kafka cluster. You have a whole heap of producers producing into loads of consumers. And that cluster there is a collection of nodes. So Kafka, straight from the off, is a hugely distributed system. Every layer is built to increase the amount you can build concurrency in, the increase the amount you can distribute out. You can have multi-producers, multi-consumers. The cluster itself can just have arbitrarily scaled numbers of machines inside it to store the data. It is absolutely amazing. And then it's built on top of Zookeeper, which manages your failure states. So this manages lead acquisition, for example. If one machine goes down, Zookeeper just instantly assigns the next one to lead the cluster and everything is fine. Zookeeper does some other really neat things. You can actually pass off, we'll talk about consumers and producers in a bit, but you can pass off even things like some of the work that the consumer has to do to Zookeeper. Having said that, Zookeeper is also the main point of failure for people when they're running DevOps for Kafka. If you look at Stack Overflow and you look at Kafka, 99% of the threads are people going, I can't get Zookeeper working. So it has some issues, but it is still a nice piece of technology. So when we talk about Kafka, we mainly talk about one abstraction. Kafka only really provides one abstraction for the data it's piping through it, and that is topics. So topics are really cool, and this is what a topic looks like. Essentially, they are just categories of message. So you would use to say, like, for example, for us, we would have maybe a topic for transactions, all the transactions going through. And inside a topic, you divide it into a partition. And these partitions are just logs. They're just message logs. You just put things on the end, and they come off the other end. Really simple. But this has some really interesting semantics. So as I said, they're categories of messages, and we have these partitions. And those partitions are split by machine. So a topic with 3 partitions may be split across 3 machines, for example. But where Kafka gets really fun is that Kafka has no rules of topic writing. You can write all your topic. If you had a topic with 3 partitions, you could write all your messages just one if you wanted to. Or you can split it evenly across all of them. You can write however makes most sense to you. All that matters about those messages is that they're given an offset. So each message written to a petition is given the offset within that petition, and your consumers can just say, okay, I last consumed from petition 1, from offset 1, I'm now going to do 2, and just step along it like that. And the main thing which made Kafka advantageous over PGQ is that they're deleted after a time set by the user, not some arbitrary time. So the default is 30 minutes. We increased that to just as high as it would let us. And we just persist those forever, and it's great. They just stay around for as long as we like. And Kafka doesn't care. Its performance semantics aren't affected by the amount of data you have inside it. As long as there is disk space, Kafka will run at the same speed. It's lovely. And then the other neat thing, I don't know, I think I've got, okay, unopinionated consumption. So this is a bit of what so as I was saying, we just changed it up a lot. So we just changed it up to 168 hours. Interestingly, apparently, like Kafka config logs can contain incredibly proprietary information. So this is all I can show you from our config log. And then this is another interesting thing here. We've got the maximum size of a log segment. Oh wait, that's not the one. Hang on a second. That's not the one I wanted. Oh, we go. There we go. Segments don't drop below this. So we have a minimum size for the log segments. So each log segment that's inside a petition has a minimum size. Because although Kafka performance doesn't decrease with the amount of space you're taking up, your consumer performance could be impacted if, for example, you have unevenly distributed data. If you've got a petition with a message in it that's massive and the next one's empty, and you've got like one petition queue with much smaller data than the other one, that could cause some issues further down the line. So you want to you want to make sure that your petition logs are all reasonably spread out and that the size is consistent amongst them. So we put in a minimum there to ensure that each message written to a petition is a reasonable size. So I said there's unopinionated consumption. There's some other really neat properties of Kafka. Because you're just the only thing the messages have is that offset, you can replay data. So if my consumer has consumed along offset like between 1 and 10, and then we get to like 10, and we realize that although we've been consuming, we haven't been able to process that, and we've lost like 3 messages, we just rewind the offset and run the consummation again. And because we're holding on to messages for so long, that data is likely to still be there. Next is strongly ordered semantics. So it is strongly ordered, which is obviously very advantageous for us because we're dealing with like payment transaction data. We don't want a refund to end up in the database before the transaction has, right? But that's only by partition. So a large part of the meat of this talk is us talking about how we actually how we abused Kafka's unopinionatedness for our domain, how we were able to make use of these abstractions to suit what we wanted to do with it. And a big part of that is because we need the strongly orderedness, we structured our topics somewhat differently to what may be recommended. So, cool. So we have this structure now. So we have Kafka in the middle, Redshift, Elasticsearch, and PGQ is still around. As Marcus pointed out in his talk earlier, if you missed it, Kafka is actually more of a piping system. PGQ is still the queuing system we're using to get the events off the Postgres database and then send them into Kafka, where they are piped through to our Redshift data warehouse and Elasticsearch. So to tell you a bit more about how we actually use Kafka, I have to tell you a bit about the payment gateway. So the payment gateway is the center of any payments processor. They have a gateway which basically handles all the important business. And in that gateway, we have databases sharded by merchant. Obviously, this isn't true for massive merchants like Uber, but that's not important. So in theory, every merchant has their own shard, and those the petitions in Kafka are fed by a shard. So if we have a topic with for example, we have a topic with 3 petitions, each one of those petitions will be an individual merchant. That gives us a strong ordering per merchant that we need to make sure their transaction data is coming in the right order. And as I said before, like refunds aren't coming before a sale, stuff like that. So then if we've got the petitions being per merchant, what is the topic? What is the category of message that we're using that abstraction for? And this is actually where we get back to the thing I mentioned earlier about Redshift and Elasticsearch being slightly different in their requirements for data, in that we can categorize not by what the data is, but by the semantics of that data. So for example, Redshift needs the shape of the data. It needs the SQL to be exactly the same. It needs the same tables, the same whatever it needs. So with that, we're literally just taking the raw Postgres events and have a topic for those. Whereas Elasticsearch needs meaning. It needs our domain-specific events. It needs a transaction sale, it needs a transaction refund, it needs a customer create, a customer whatever. So we end up with 2 topics. We end up with a data stream and an event stream. The data stream is just raw SQL, the event stream is the semantic data that's more interesting. So cool, at this point, job done. We've architected this thing, so we have to build it. And that's where Clojure comes in. So the first question, being a Ruby shop, is why would you use Clojure? We used Rails, we have no experience with Lisp, we've never had any experience with JVM, and if you're using the JVM regularly, you know it takes a bit of tuning. So the first argument is actually because of the JVM. So all those technologies I've mentioned, Kafka, Zookeeper, Elasticsearch, they're all JVM technologies. And aside from Elasticsearch, which has a HTTP API, there's actually no native API, no native SDK outside of the JVM for those. There is third-party libraries for Kafka and Zookeeper, but they're not maintained by the main maintainers of those technologies. And as a company which has to be secure all the time, as a company that wants to be up to date all the time, that's an extremely risky proposition. We need the first-party helper libraries. So, and the next one is laziness. As a Haskell, I'm a huge fan of laziness. So laziness, if you're not aware what it is, basically it's delaying the evaluation of expressions. So if I were to do an arithmetic expression like 1 + 2 × 5, I would see the 1 + 2 and I'd go, oh, I don't need the result of that now. Store that as a func. Move on to the next bit. Oh, ×5. Okay, ×5 times this func. We don't need any of this right now. Let's just leave this over here. And then later on when I want to output that, I'll come back and say, oh, okay, now I need to put these things together. Which sounds stupid, but it has really awesome properties. For example, infinite data structures. Without laziness, you can't have infinite data structures. If I've got a list of 100 billion elements and I want the 6th one in a non-lazy environment, that's just it's gonna try and compute the whole list before I get that 6th element. That's ridiculous. With laziness, we just get to the 6th. We don't bother evaluating the rest. So, lazy streams. That's where we came useful. So this is some Clojure, obviously. This is actually a macro, so I'm going to expand that. So with this Clojure, essentially what we're doing here is this is part of our consumer. So we are consuming messages from a given topic, and then we're passing those messages to our processor. The neat thing here is that because it is an infinite lazy stream, we don't have, notice how small that is. We don't have any logic for, is there still meshes on the queue? If yes, consume. If no, do this. We don't have any logic for blocking at the end of the queue. We don't have any logic for handling race conditions. It's all just handled for us by infinite lazy streams, which also makes testing very easy. Because, for example, so they ran into this ridiculous issue, right, where they were testing the consumer, and they were expecting, the test was expecting free queue messages to come through the system, but it was a lazy data structure. So 2 messages came through, because at one point one of them wasn't making it into the queue at another end of the test. 2 messages came through, but then it's lazy, so it just sits and waits for the next message. No output, no errors. So the test wasn't finishing, no outputs, no errors. It was just waiting politely for this next message to get there. And it was never going to get there because it was a testing setup. There was no more data coming in. So they were just sat waiting there for a minute going, this test is taking a while. No idea what to do about this. So they ended it, and then because they had no output, they had to go through all the code and try and figure out what could have possibly have happened. Where did that stray message go? But because Clojure is fairly good with polymorphism, with genericity, and with not really caring where you put which data structure where, in this example, they're able to just swap out that lazy data structure. So instead of having the lazy data structure for the test, they just swap it out with a defined length list. So we know the length of the list. We just run the test on that. We can just swap those data structures out ad hoc as need be, which is really neat. So the next thing is concurrency. So obviously Clojure is one of those languages that's been built with concurrency in mind from the ground up, as many of the new languages are now, Go, etc. So when trying to build a system like this, like the concurrency aspects are really important. So we started with looking at the different alternatives and what we could use. So obviously threads is the first one. And using threads, we were looking at basically having each partition being fed by a thread and then being consumed by a single thread. But then we had some issues there, which is the shutdown logic. If we want to shut down the whole system, we need to go make sure that a thread is ready to finish and that it's not still consuming, and then communicate that between all the threads. It just turns into a huge mess, and it results in, okay, one thread's not ready, finish up your processing, wait for that thread again, signal to the others that it's now ready to shut down. Oh no, this other thread's not ready. So we abandoned that solution because it was also very heavy. Threads are quite a high level abstraction. They take a lot to do. So we then moved on to Go routines. So Go routines are green threads, and you can spin out many, many more of these, which enabled us to do something a bit more fun. So the consumers were still running on a single thread, but the what would pull the process running on a single thread, and then we would pull each merchant's data off of a partition with a green thread with a Go routine and pass that into the producer, which was the processor, which was a thread. And these were great. These were a lot better. Go routines have some facilities for signaling in between. Because they're green and you can run many more of them, this was much more efficient. But again, we still have that shutdown logic problem. There was no neat solution for that. And then come actors. So actors are actually an Erlang abstraction, and they are wonderful. So our actors are being produced by Pulsar. You may also be familiar with Akka if you've been in the talks today. So Pulsar is a open source actor library built on top of another one, which I think is called Quasar. Really great, well worth looking at. And the neat thing about actors is they're built in shutdown logic. They're also built in statuses. So actors have this really neat thing called, I can't remember what it's called. It's like tasks or something. But basically, actors have capability to have logic included, which is widely used. So if there's someone in these, so someone at some point was having to handle lots of shutdown logic with actors. And they were like, okay, this is a common task for actors. So they can spin that out, and other actor users can use them. So we had built-in shutdown logic. We had the ability to status really easily. And this enabled us to also make some really neat things. So we had an actor for a single merchant. So each merchant has their own actor. The actor is able to signal the status of that merchant at all times. The actor is able to signal to other actors that it's ready to shut down. And those actors are feeding our single process thread, which is assigned to each topic. So we end up with a really, really nice system. And it also enables us to offload work to Kafka. Because each petition has an actor, if the process thread is not ready, it just signals to the actor signals to the producer, and the producer slows down in producing. Kafka, the consumer, stops consuming. And that allows us to put more work back into Kafka, more work back into Zookeeper, which is really, really nice. It also fits very well, I'm not going to go into this, but Elasticsearch has an abstraction called aliases, which are essentially identical to actors. So it's a really nice, neatly packaged solution having all these together. So what did we learn from that? So a couple of things we learned. First of all, that garbage collection is absolutely just pivotal in this whole thing working. You want to keep the garbage collection interval small. So we were using a new technology, a new garbage collector called G1GC, garbage first garbage collection, which is a controversial one because lots of people are getting runtime errors with it. But we're having fun. Apparently, I had a guy from Elasticsearch come talk to me at a previous place I gave this talk, actually from Elasticsearch, saying G1GC doesn't work with Elasticsearch at all. And I'm like, well, it does. Clearly. Sorry. So yeah, that's fun. G1GC is really nice. There is currently a big argument in Java community about the fact that it's become the default, but whatever. So next one's obviously heap size is important. And somewhat contrary to what you might think, we found that small is actually better. And this is due to using Clojure. So Clojure obviously has a really neat library of mutable data structures. The thing with mutability is you creating a lot of objects and they very rapidly blow the heap. So to keep that garbage collection interval small, you want smaller heap sizes. The next one is monitor all the things. The neatest thing we had, there's a typo in the next slide. The nicest thing we had from all of these systems, from using actors, from using Kafka and using the JVM, is that we were able to do a lot more monitoring. So by using the JVM, we were able to use JMX. Our actors can test the statuses all the time. So we're able to much more reliably tell the status of our system, which is able to help us prevent split brains in our Elasticsearch instances, which was previously something we had a crippling problem with. And then obviously don't use the dealt, it's meant to be default configs. If we use default configs, we wouldn't have solved our original problem. We'd still be on the 30-minute timeouts for the data, which is awful. And you also find that when you're using the JVM at scale, you need to do a lot of minute tuning on JVM configs. Yeah, there's a lot of weird things like heaps that you need to think into. Is anyone using the JVM at scale? Just one. Cool. That's unusual. JVM scales very well, by the way. So, and then finally, use a good concurrency model. We took the time to sift through every concurrency model and try every one. We didn't just go by the advice and Stack Overflow. We tried out each one, actually tried how it worked with our data, with our system, what advantages we had from structuring the way we consumed and processed, etc. Future gains are the really interesting stuff. So obviously we now have a real-time source of truth. We have a source of truth which is updated constantly, which enables some really cool things. So not only can we do real-time reporting, we can do real-time fraud monitoring. So there's this really horrible thing that people do where they stolen credit cards, right? They get these, when people steal credit cards, they don't just sell them in individuals. They go and get gigantic batches of tens of thousands of them, and then they sell them in auctions. So when they gather these batches up, before they sell them, they have to test they all work. So merchants get hit every now, it's completely potluck. One day you'll be sitting there on the other end of your home business with a checkout, and suddenly you'll be getting like 20,000 transactions. And you'll be like, oh, this looks great. I'm getting so much business today. No, it's just a credit card fraudster testing all their cards. And then you'll start getting chargebacks in mass numbers. So we can actually start to see these waves. If we've got a merchant who's normally getting 800 transactions per day, and suddenly within the space of 1 hour, they're getting hit by 20,000 credit cards all from the same IP, we're just looking at that going, well, something's going on here. And we can see that live, and we can react to that. We can help that merchant out. We can start to alert the bank this is happening, so they're not as impacted by chargebacks. Because if you've got something fraudulent happening and someone does call their bank and says there's a chargeback, that really impacts your credit score. That's not a good thing. So we can start to support that. And we get real-time reporting as well. Obviously, that's the most important one. When we go back to that search feature, merchants can now go search on their data straight away, and they get back exactly what they should do without any of the cruft we had before, without having to divide their search query down by loads, and then get that in real time. I can go look up a transaction that happened 20 seconds ago, and that's not impacting our ability to do live transactions. And obviously, this impacts our future Clojure stack. So having just been a Rails shop with a bit of Go, we're now able to confidently build Clojure. And actually, I hope it's on film, so I hope this is public. It's on a public docs, hidden, but it's there. So, for example, if you look at Pinterest with their Bible pins, so how the Bible pins are working is Pinterest present you the checkout, but then they take your credit card and they pass that on. So if I buy something from Amazon through Pinterest, I don't think that's a thing, but if I did, I put my details in the Pinterest, Pinterest would then take that credit card and pass it into Amazon's system. When you look at Braintree, we're explicitly designed not to do that. Like merchants never get your credit card. They just get a token that represents it. We keep your credit card. So to work with Pinterest Bible pins, we had to create a system where Pinterest were able to pull out credit cards and provide those in whatever weird format was needed to whatever database, to whatever third-party checkout. So we wrote a programming language with a type system, I might add. They wrote a type system for this in Clojure to serve this API. And that is awesome. And that happened because of this project. So that's pretty much everything. Thank you. I've been Joe Nash.